Good evening, everyone. My name is Hafiza Maqsood. Today I will be presenting my research paper on titled Thermal Sensors on Cellulose-based Substrate for Green Thin Film Electronics. Let's begin with the fascinating field of flexible electronics reshaping the future of technology. Unlike rigid electronics, they can be imperceptible, that the electronic devices can be so thin and that they become invisible. They can be stretchable and bendable without losing their functionality. They can become wearable when on a human body, and they can cover large areas seamlessly from wearable sensors to foldable displays. But with this rising adoption, there comes a major concern, that is electronic waste. As you can see in the chart, how globally electronic waste management system market is expected to triple by 2030, reaching over 160 billions. There one effective way to reduce the electronic waste, there must be a balance between the ecological protection and the electronic development. Let's talk about what we have been using traditionally, some plastic substrates like polyamide and the Petti. As a matter of fact, these plastic substrates are non-biodegradable and contribute significantly to the electronic waste. That's why there have been a big shift now towards the sustainable and the green materials. Some of the exciting examples include gelatin, paper, silk, mother of pearl, and there are still some limitation in these materials in terms of the moisture sensitivity, in terms of the mechanical limitations. But still, this is a big step toward sustainable and the sustainable futures, marking another demonstration of this platform to introduce triacetyl cellulose, a nature derived materials often derived from plants like cotton, wood, and it is the most abundant organic biopolymers found in on Earth. Thanks to its flexibility and high optical clarity, that serves as an excellent substrate which helps to minimize the electronic waste and also helps to sustain the future. We use the tech substrate, and before any fabrication, the properties of the tech substrate were evaluated. First, we measured the transparency factor in comparison with the polyamide and the peak. Tech showed 93% transparency. In addition, we measured the atomic force. We did the AFM measurements. Its value is 1.7 nanometer, low surface roughness, that is very ideal for electronic application. And then we also checked the dissolvability of the substrate in different liquid media, and it was found that that substrate is soluble in organic solvents. So it suggests the alternative needs of the some cleaning agents and the etching solutions. We fabricated two types of temperature sensors. One is RTD, and for sharp application, we start with 80 micrometer thick tech substrates, and then we sputtered 100 nanometer copper as electrodes, and we use the shadow mask to define the deposition areas. Here you can see the multiple geometries of the RTD, the design flexibility and pattern integrity demonstrate the scalable production, and the micrograph of the RTD shows the defined edges and the uniform deposition of the metal layer. To verify electrical performance, we conducted IV measurements, and the resulting behavior is linear and symmetric, and the measured resistance values to be 74 ohms. For the fabrication of the thermistor sensor, again we start with 80 micrometer tech substrates, and we sputtered 100 nanometer molybdenum as electrodes, and then we sputtered 50 nanometer IGZO due to its semiconducting and temperature sensing applications. The schematic shows a simple layout of IGZO and the molybdenum contact, and also the micrograph shows a continuous film coverage without any breaking. And we again measured the IV measurements, and the result is linear and symmetric, and the value of the resistance to be around 5 kilo-ohm. The electrical characterization was performed by using a custom design setup. First, we performed a heating cooling test where we continuously increase temperature from 25 to 75 degrees, and a linear trend is reported between temperature and the between the resistance and the temperature. Then we performed the damping test where the temperature was increased in the discrete manners and then decreased. The sensor followed the trend smoothly without feedback and or the distortion. And then we perform the cyclic test, where the temperature was increased and then reversed. In order to see the sensor show a very stable and the reliable performance under all of these tests, and the calculated average response time of the sensors to be 110 seconds. That is quite reasonable on this type of passive device and on this type of the polymeric substrates. For the characterization of the thermistor, we follow the cooling heating protocol instead of heating cooling protocol in order to ensure the reliability of our sensor. So here a non-linear trend is reported, which is attributed to the RGZO due to its negative coefficient of resistance, and unvisible hysteresis was observed, which is likely due to the polymeric nature of the substrate. And again, we perform the damping test, where the temperature was increased in a discrete manner, and also the cyclic test, we perform 5-step cyclic test, where temperature increased and then reversed. So in this way, our result was quite consistent in both these performance, where show the sensor reliability even under continuous and the discrete changes of the temperature. In order to study the mechanical properties, we also performed the bending test at different bending radii with a minimum radii of 8 mm. So the strain was calculated at each bending radii, and there is, as you can see in the plot, there is a bit increase in the resistance during bending of the RTDs, which is likely due to strain-induced deformation causing the copper to become more resistive while bending. And for the thermistor, we started from a 16 mm and ends at 8 mm. And you can see in the plot there is a by decrease in the resistance, which is likely due to when the thermistor bending RGZO increases properties and decrease the electric resistance of the sensors. At the end, in order to study the transient nature of the thermistor sensors, we performed the dissolution analysis. Again, a custom design setup was used. And on the day 0, initial functionality was measured. The value of the resistance was 5 kilo ohm. And then with the passage of the time, the material degradation was measured. And it was clearly see the material start to the dissolve. And on the day 10, the sensor showed the complete electrical failure. Its resistance was approaching 100 mega ohm, indicating open circuit. So two types of temperature sensors were studied on that substrate: resistance temperature detectors and the thermistor sensor. So future studies will focus to modulate the dissolution analysis. So we can fabricate electronics with a controllable devices lifetime, as well as the reusability of this test substrate for another microfabrication runs for some active devices like thin film transistors and the circuits. That's all. Thank you so much.